What is an operating system? The operating system, also known as OS, as a fundamental software that manages all hardware and software, acting as a bridge between you, the user, and the computer. It provides the base upon which all your programs run, ensuring effective communication. OS has the rich history that spans for a long time, since 90s. We already have different generations of OS, from the first in 1945 to 1995, which used vacuum tubes and plugboards. Here is a little summary of what the OS has been through to develop what we have in the present. In the first generation of computers, there were no operating system. Programmers interacted directly with the hardware, writing code in the machine language to perform simple calculation. The second generation saw the arrival of the first operating system like GMOS, created by General Motors in the early 1950s. This system used batch processing, handling jobs sequentially via punch card. The third generation from 1965 to 1980 brought integrated circuits and multi-programming, allowing multiple tasks to run concurrently, making systems far more efficient. Finally, the fourth generation from 1980 onward is defined by personal computers and the rise of user-friendly graphical interfaces. Operating systems like Windows and Mac OS made computing accessible to everyone. It also keeps track on how much time and resources each program uses. The system incorporates error detection mechanism, including error messages and debugging utilities to facilitate problems identification and resolution. The OS manages your computer's memory, allocating it to different programs as needed. Many characteristics of an OS exist to provide for the needs of the user. First, it manages all your devices, your keyboard, mouse, printer, and more. It acts as an I/O controller, scheduling their use efficiently. Next, it handles file management, controlling access to your files and folders, ensuring the right programs and user get resources they need. It also manages the CPU, assigning it to programs efficiently. It constantly monitors performance, tracking response times to ensure everything runs smoothly. For further information and familiarization, here are some examples of operating systems that are often used and integrated. Microsoft has developed and marketed several popular commercial operating systems, including paid versions like Windows 8, Windows 10, and Windows 11. Additionally, there is Unix-based operating system that was first released by Linus Torvalds on September 17, 1991 and is well loved by users. Apple has developed and marketed the mobile operating system since 2001, designed and exclusively for its devices like iPhone and iPad. There's also another mobile operating system based on modified version of Linux kernel and open source software, primarily used for touchscreen devices such as smartphones and tablets. The operating system serves multiple essential functions, including resource management by allocating hardware for optimal performances, process management through scheduling and termination of the process, and the storage management by organizing data with various file systems. Additionally, it controls primary memory usage by tracking the allocating memory to process, while also enforcing security and privacy through authentication methods to prevent unauthorized access.
Of course, the OS cannot be utilized if it can't be used by a person. The user is the individual interacting with the computer, while system and application programs are the software that the user runs, utilizing the services provided by the operating system. Again, the operating system is an essential software that manages a computer's hardware and serves applications by translating user requests and application needs into hardware commands. Hardware refers to the physical components of the computer, including the CPU, memory, storage, and input-output devices. Here, we have the basic elements. The CPU, or Central Processing Unit, is the brain of your computer. It directs all operations, and handles all the data processing. The main memory or RAM stores data and programs while your computer is on, but everything is erased when you turned it off. It's also called primary memory. Input-output modules serve as the central communication interface for a computer system, facilitating the transfer of data between the system's internal components and external peripherals, including keyboards, mouse, monitors, and hard disk drives. Lastly, the system bus. The system bus is the central communication pathway within your computer. It enables data transfer between the CPU, main memory, and input-output modules, making it possible for all the components to work together. Here, we have an image that depicts a simplified diagram of a computer's architecture, focusing on the connection between the CPU, memory, and various devices. The computer's brain, the CPU, gets instructions from memory or RAM and executes them. RAM is the CPU's workspace, holding the instructions and data. To interact with external devices like your keyboard, mouse, and monitor, the CPU uses device controllers. The central processing unit, or the CPU, is the brain of the computer, responsible for executing instructions, while memory refers to the computer's main memory, where currently running programs and their data are stored. We also have the device controllers, which from the name itself controls different devices. These controllers manage hard disk drives by handling data reading and writing, while USB controllers oversee communication with USB devices such as keyboards, microphones, and external drives. Video adapters manage video display by sending signals to the monitor to display images and text. It all starts with an input and output request. The CPU reading data from a device like a hard drive or keyboard initiates the request. The data is then transferred. It might go straight to the CPU or stop at the cache first for faster access. Once the device finishes its job, it signals the CPU with an interrupt. The CPU then processes the data, a part of the instruction execution cycle. Finally, the CPU sends the processed data and any new instructions back to memory for storage or for further processing.
This scheduling, also called I/O scheduling, is how operating system decide the order for handling disk input and output requests. The goal is to make these operations faster, cut down on access time, and keep the system running smoothly. In this scheduling, there is what we call disk geometry, which refers to the physical structure of a magnetic disk drive that contains the data or request. Inside this structure, there are tracks, which are circular paths on each platter resembling rings that enable the retrieval and storage of data. Sectors are what divides tracks, holding a fixed amount of data, be it 512 or 4096 bytes. This improves the data management and retrieval. Cylinders are tracks but vertically oriented. This allowed the read-write head access the same track for multiple platters in one go. Another terminology for the disk scheduling is a disk access time. It is the total time to locate and retrieve data. It includes the following: seek time, transfer time, and rotational latency. Seek time is the duration for the read-write head to reach the correct track, while transfer time is the wait for the desired sector to rotate under the head, influenced by rotation speed. Rotational latency is the time needed to read or write data at the correct sector, depending on the disk data transfer rate. For the I/O request queue, a disk controller manages it, each specifying a track number, and uses a scheduling algorithm to determine the order in which they are processed. The operating system uses this scheduling to determine the next request to execute, which involves two types of time: CPU time for executing processes on the CPU, and I/O time for accessing input or output devices. Scheduling algorithms aim for fairness, high throughput, and minimal read-write head travel time. For our initial scheduling algorithm, first come first serve or FCFS, the simplest disk scheduling algorithm that processes I/O requests in the order they arrive without reordering based on track numbers. Consider a disk with 200 tracks and the following I/O requests in the queue: 45, 80, 25, 90, 60. The disk head is initially at track 50. Using the FCS disk scheduling algorithm, calculate the total seek time to process all the requests. Here is the video to further explain how this algorithm works.
For the disk scheduling algorithm, first come first served, we shall now consider a disk with 200 tracks and the following I/O requests in the queue: 45, 80, 25, 90, and 60. Here. The disk head is initially at track 50. So now we will calculate as well the total seek time to process all of the requests. So right now, we will start at 50. Since our disk head is initially at track 50 as stated in the problem, we will simply follow the queue given. So from 50, we will now go to 45. That's right here. And now after 45, we will go to 80. After that, we will go to 25. And after 25, we will simply go to 90. And after that, after 90, we will go to 60, our last process. Here, we just simply have to follow the queue of the request given, right here, the cubed. Now, for computing the total overhead movement or the total distance covered by the disk arm, we need to perform simple addition and subtraction. Starting from 50, get down. Starting from 50, since that is where the disk head is, we will subtract 45 and add the next pair. Okay, remember to use the previous request we just used for the next pair. So we will just simply have to follow the graph for computation. 80 minus 45 plus 80 minus 25, because from here you went to here, plus 90 minus 25, and lastly 90 minus 60. So, computing all of that, we will have a total distance covered of 190.
Advantages of this approach include ease of implementation and fairness by processing requests in the order received. However, it can lead to inefficient disk access with long seek time if requests are scattered, and performance may suffer with significant variance in track numbers. Next, shortest seek time first or SSTF selects the disk I/O request closest to the current head position, minimizing the seek time for each request. Considering a disk with 200 tracks and the following I/O requests in a queue: 45, 80, 25, 90, 60. The disk head is initially at track 50. Using the SSTF disk scheduling algorithm, calculate the total seek time to process all the requests. Here is a video to further explain how this algorithm works.
The shortest seek time first, we shall now consider as well a disk with 200 tracks and the following I/O requests in the queue: 45, 80, 25, 90, and 60. The disk head is again initially at the track 50. We will calculate the total seek time to process all of the requests. So here, starting at 50 as well, since our disk head is again initially at track 50. Now, to determine the next request to queue, we will have to consider which is the closest to 50. Here, 45 is closer to 50 than it is to 60. So we will go to 45 now. So I will give you a tip for knowing which request to process first or to process next. So you can just simply subtract 50 to 45. So here, 50 minus 45. It is gonna give you A5. And again, to compare as well, 60 to 50. Which will give you A10. There, you will easily determine which one is closer. So in this case, it is obvious that it is 45, which is because it gives us 5. There. So now to continue, you can just repeat the same process until you reach the last request in the queue. If there is any request left, you can simply jump to it and the process ends. So here, 50 to 45. So which one is closer to 45 right now? Is it 25 or 60? Of course, we can see that it is 60. So we will go to 60. So again, if there is any request left, you can simply jump to it and the process ends. So here we have 25 left. So from 90, we will go to 25. For computing the total overhead movement or the total distance covered by the disk arm, we need to perform again the simple addition and subtraction. Starting from 50, since that is where the disk head is, we will subtract 45. And add the next pair. From 50, 45, 60. So 60 minus 45 plus 80 minus 60 plus 90 minus 80 plus 90 minus 25. We will just simply follow the graph we just made to know which value we will use next. So here, we just followed it. 50, 45, to 60, to 80, to 90, and to 25. The answer for that is, we will have an answer of 115.
This approach reduces seek time and improves performance compared to first come first serve or FCFS in many scenarios. However, it can result in starvation for distant requests and is less predictable since the order of servicing depends on proximity rather than arrival time.
We now have scan, also known as the elevator algorithm, works like an elevator with the disk head moving in one direction, processing requests the reversing direction at the disk end. Considering a disk with 200 tracks and the following I/O requests in the queue: 45, 80, 25, 90, 60. The disk head is initially at track 50 and is moving towards the outer tracks. Using the scan disk scheduling algorithm, calculate the total seek time to process all the requests. Here is a video to further explain how this algorithm works.
So now for the scan or elevator algorithm, using the same given from the previous algorithms, we will start again at the disk head. So our disk head is 50. And we were gonna be moving towards the outer tracks or the higher numbers as we called. So 50. And as we are going to the outer tracks, we go to 60 here. We go to 80. And 90. There. So here, as we are in 90, since it will only be moving in one direction, we will process those first. So from 50 to 60 to 80 and to 90 until we reach the end of the disk, where we will go to 199. We'll go to 199, and after this we will reverse back to process the leftover request, which is 45 and 25. We will service them as we go back. So here we go to 45 first. And we will end the process at 25. So here at 25. There. So for our computation, almost similar to the previous algorithms that we just computed or just performed, we just also need to follow the graph we made to know which values will be used. So from 50, it will start at 50 actually. Start at 50 minus 60. But this time, we should have a positive value. So 60 minus 50 plus 80 minus 60 plus 90 minus 80. And then we should also include the 199 since it was used in the graph or in this algorithm. So 199 minus 90. And again, 199 minus 45 since we went to 45, right? Minus 45 plus 45 minus 25. So we will have a final answer of 323. Here.
This approach offers uniform wait times and prevents starvation of edge requests. However, it results in longer seek time when returning to the start and incurs higher overhead due to the return job. Circular scan, also an elevator algorithm. This algorithm serves requests in one direction only. When the disk arm reaches the end of the disk, it returns to the beginning without servicing any requests on the return trip. This approach treats the disk as a circular list, ensuring more uniform wait times. Consider a disk with 200 tracks and the following I/O requests in the queue: 45, 80, 25, 90, 60. The disk head is initially at track 50 and is moving towards the outer track. Using the C-scan disk scheduling algorithm, calculate the total seek time to process all the requests. Here is a video to further explain how this algorithm works.
Now, we will be computing for the circular scan or elevator algorithm. This is actually a type of scan. So again, we will be using the same given. So again, this is similar but a little different from the scan algorithm. Here, we will not be servicing requests that we will pass through as we reverse back. So after 199, we will jump to 0 and go upward again until we reach 25 and finish the progress at 45. So I will simply show you. So again, we will be moving towards the outer tracks. So 50, since that is where the disk head is. Track 50 to 60 to 80 to 90, and we will go to 199. So instead of going to 45 or 25, we will go first to 0. There. Then from then on, we will go process 25. Process at 45. Here we go. So again, for the computation, again, almost similar to the previous algorithms, we just also need to follow the graph we made to know which values will be used. So here, we will start at T. So 60 minus 50. Remember that the result should always be positive or an absolute value. So 80 minus 60 plus 90 minus 80 plus 199 minus 90. And we will include the 199 and 0 as well for the computation since we passed through them. So 25 minus 0 plus 45 minus 25. So there we go. So here, we will have a final answer of 480.
This approach offers uniform wait times and prevents starvation of edge requests. However, it results in longer seek times and returning to the start and incurs higher overhead due to the return job. Look algorithm services this request by moving a disk arm only as far as the last request in one direction before reversing. It looks ahead to see if there are pending requests and avoids unnecessary travel. Consider a disk with 200 tracks and the following I/O requests in the queue: 82, 170, 43, 140, and 24. The disk head is initially at track 50 and is moving towards the inside track. Here is a video to further explain how this algorithm works.
Okay, so for the look algorithm, we will have a different given for this algorithm. So the problem, consider a disk with 200 tracks and the following I/O requests in the queue: 82, 170, 43, 140, and 24. The disk head is initially at track 50 and is moving towards the inside tracks. So how we will also calculate the total seek time to process all of the requests. The look algorithm is a lot similar to scan actually, but here, we will not be passing through the last track. After reaching 170, we will immediately reverse back and service 43 and 24. So here I will show you. Oh wait, I did not include 50, so we will write 50 here between 43 and 82. So 50, we will start at 50. So 50, we will go to 82. 82, 140, 170. So again, since it is a lot similar to scan, but we will not be passing through 199. So instead, we will service back immediately after 170. We will go to 43 immediately. We will jump to 43. There. And end the process at 24. There we go. Right, that is correct. So now we will also, for the computation again, we will also need to follow the graph. From 50 minus 82. So 82 minus 50 plus 140 minus 82 plus 170 minus 140 and go to 43. So 170 minus 43 plus 43 minus 24. And there we go. Let us compute for this one. So for this one, we will have 266. There we go.
This approach reduces unnecessary movement and is more efficient than scan. However, it is not entirely fair and may lead to higher wait times for distant requests. C-look algorithm is a variation of look, where the disk arm moves only between the outermost requests in one direction, then jumps back to the beginning without servicing requests on the return trip. Consider a disk with 200 tracks. And the following I/O requests in the queue: 82, 170, 43, 140, and 24. The disk head is initially at track 50 and is moving towards the inside tracks. Using the C-look disk scheduling algorithm, calculate the total seek time to process all the requests. Here is the video to further explain how this algorithm works.
Okay, for the circular look algorithm, so we will now be using the previous given as well. The circular look algorithm is a lot similar to C-scan or circular scan algorithm, just like look and scan algorithm, you know. But here, we will not be passing through the last track as well. Upon reaching 70, we will not jump back to 0, but instead jump 24 until we reach and end the process at 45. So here, again, we will start at 50. We will go to 82, 140, and 170. There. So here, instead of passing to 43 first, we will go to 24 immediately. And then end the process at 43. So there. As you can see, it's similar to C-scan or circular scan, but we did not pass through 0 nor 199. Okay, for its computation, again, we just have to follow the graph that we just made. So 82 minus 50 plus 140 minus 82. plus 170 minus 140 plus 170 to 24. So 170 minus 24 and 43 minus 24. Here we go. So here we will have the final answer of 285. There we go. That is for circular look algorithm.
This approach reduces response time variance and avoids unnecessary head movement. However, it results in a longer seek times when returning to the beginning and incurs overhead from the backtracking.
Now, we will move on and discuss CPU scheduling and how it works. CPU scheduling is a crucial operating system function that manages CPU time allocation to processes. Its goal is to maximize CPU utilization while ensuring efficient and fair execution of tasks. We will also have its process execution cycle, which defines its implementation. A CPU burst is the time a process actively executes on the CPU, varying based on computing demands, while an I/O burst occurs when a process waits for I/O operations, typically shorter than CPU burst. The final CPU burst is the last execution phase before a process terminates, after which it releases sources. Processes cycle through different states: new, ready, running, waiting, terminated, with the scheduler allocating CPU to ready processes. Context switching, saving and loading process states incurs overhead. Time-sharing systems use time quantum to ensure fair CPU location. Preemptive scheduling allows the OS to interrupt processes for responsiveness, while non-preemptive scheduling lets processes run until completion or voluntary yielding, potentially causing inefficiencies. The dispatcher is the component responsible for executing the scheduling decisions made by the CPU scheduler, while dispatcher latency refers to the time taken to stop one process and start another. The long-term scheduler manages multitasking by balancing I/O and CPU-bound tasks to reduce execution frequency. The medium-term scheduler controls multiprogramming through memory substitution operations occurring every few milliseconds. The short-term scheduler optimizes CPU usage by selecting processes from the ready queue for immediate execution to ensure quick performance response. The process manages multitasking by swapping programs in and out of memory to optimize memory usage and performance by balancing I/O and CPU-bound operations. First come, first serve, or FCFS, is a simple CPU scheduling algorithm where processes are executed in the order they arrive in the ready queue. The advantages of FCFS includes its simplicity and the order in which processes are served. However, it has drawbacks such as longer waiting times for short processes and being unsuitable for time-sharing systems that need quick response times. The shortest job first, or SJF, is a scheduling policy that prioritizes executing the waiting processes with the shortest execution time and can be either preemptive or non-preemptive. For the shortest job first, the priority will always be the shortest burst time. P0 will arrive at 3 millisecond, P1 at 5 millisecond, P2 at 8 millisecond, P3 at 0 millisecond, and P4 at 12 milliseconds. This means that P3 will be the first one in the execution, and when you encounter two processes that have the same burst time, just refer to the time that it arrived. Thus, P0 will be next, then P2, P4, and P1. As explained earlier, the completion time of the processes are as follows: 11, 30, 15, 7, and 21. As for their turnaround time, it is 8, 25, 7, 7, and 9. For the waiting time, it is 4 milliseconds, 16, 3, 0, and 3, which is same as the response time. The advantages of SJF, including minimizing the average waiting time for processes. However, it has a disadvantage of potentially causing starvation, where longer processes may await indefinitely if shorter ones continuously arrive. Shortest remaining time first, or SRTF, is the preemptive version of SJF,
where the CPU is preempted if a new process arrives with a shorter remaining execution time than the currently running process. The next one is shortest remaining job first. P4 will arrive at 0 millisecond, then P1 at 3, P2 at 5, P3 at 8, and P5 at 12. The first process that will be executed is P4, since it will arrive at 0 millisecond. And during that process, P1 will enter at 3 millisecond. P4 will process those 3 seconds, resulting in 4 milli remaining time. Thus, it will be processed again. At 5 milliseconds, P2 will enter the queue, but P2 have 9 milliseconds, so P4 will still continue to execute until it is finished. 7 milliseconds have passed and we have P1 and P2 on the queue, and P1 have a shorter burst time, so it will be processed next. P3 will enter the queue at 8 milliseconds, but since P1 has processed 1 milliseconds and there's only 3 milliseconds remaining for burst time, it will be processed. P5 will enter at 12 milliseconds and P3 will still be processed since P5 have 6 milliseconds to execute. After completing P3, P5 will follow as it has shorter burst time than P2, which is 6 to 9. The completion time of P1 will be 11, P2 is 30, P3 is 15, P4 is 7, and P5 is 21. As for the turnaround time, P1 will be 8, P2 is 25, P3 is 7, P4 is 7 as well, and P5 is 19. Lastly, as for the waiting time, P1 will have 4 milliseconds, P2 at 16 milliseconds, P3 at 3 milliseconds, P4 at 0, and P5 at 3 milliseconds. SRTF offers great responsiveness for short jobs in interactive environments, but it has disadvantages such as increased overhead from frequent context switching and the risk of starvation for longer processes. Round-robin scheduling, or RR, assigns a fixed time slice to each process in the ready queue, moving incomplete processes to the end of the queue after their time slice expires. The round-robin scheduling has some special conditions to it. The quantum time. The quantum time is the amount of time wherein it is the maximum duration of a process before being interrupted. Here, we have 4 processes, P1 at 0, P2 at 1, P3 at 0, and P4 at 3. P1 will be executed first because it is first in the queue, even if it arrived at the same time as P3. And then, after 3 seconds, all of the process will enter the queue, and P1 will be moved on the end of the queue since the quantum is only 3 seconds. Then after that, P3 will be processed as well. Since it has 6 milliburst time, it will only execute the 3 milliseconds quantum time, thus moving it on the end of the queue as well. It will be the same for P2 and P4 up until all the processes have been executed. For their completion time, P1 is completed at 32, P2 at 9, P3 at 17, and P4 at 11. Their turnaround time are as follows: 32, 8, 17, and 8. Lastly, the waiting time for P1 is at 11 millisecond, P2 at 5 millisecond, P3 at 11 millisecond, and P4 at 6 millisecond. Round-robin scheduling ensures fresh CPU time allocation for all processes and is suitable for time-sharing systems. However, it can lead to excessive context switching and potentially higher average waiting times. Priority scheduling, or PRIO, allocates a CPU to the process with the highest priority, where lower values often indicate higher priority. As for the priority scheduling, there will be certain conditions. For this example, the priority will be the arrival of the processes 3 millisecond, 4 millisecond, 2 millisecond, and 8 millisecond. The first to enter the queue will be P1 at 2 millisecond and will be completed at 7 millisecond, followed by P3 that will enter the queue at 3 millisecond and will finish at 10 millisecond, P2 at 4 millisecond, and will finish at 22 milliseconds. And lastly, P4 at 8 milliseconds and will finish at 39 milliseconds. The completion time are as follows: 7, 22, 10, and 39. As for the turnaround time, 5 milliseconds for P1, 18 for P2, 7 for P3, and 31 for P4. And the waiting time is 0 for P1, 6 for P2, 4 for P3, and 14 for P4. Priority scheduling is flexible, allowing for the prioritization of important tasks, and is useful in real-time systems for immediate task execution. However, it can cause starvation for low-priority processes and becomes more complex with dynamic priority changes. Lastly, the preemptive priority scheduling, or PPRIO, assigns priorities to tasks and allocates the CPU to the highest priority process, allowing higher priority processes to interrupt currently running processes. The preemptive priority scheduling. The priority for this algorithm is to process 1 and then 2, 3, and 4. P1 arrived at 0 millisecond, P2 at 2, P3 at 4, and P4 at 6. Since the order is just based on the process, it will be just like the first come first serve algorithm. The completion time for the processes are as follows: 12, 18, 25, and 40. As for their turnaround time, P1 at 12, P2 at 16, P3 at 21, P4 at 34, and lastly, the waiting time of P1 is at 0, P2 at 10, P3 at 14, and P4 at 19. Preemptive priority scheduling ensures quick execution and improved response times for high-priority tasks while reducing starvation risk. However, it may lead to overhead due to increased context switching and adds complexity in managing priority levels.